Okay. Hand over to Callum. Off you go.
Right. Thank you, James, and thanks to everyone for being here. I've been introduced, so I've got a fair few slides, so I might just dive straight in. This is a presentation of my thesis on experiments in geophysical compressive sensing. So compressive sensing is a pretty new sort of thing to geophysics. So I guess the main purpose behind this all was to sort of try and make sense of it so that I could code up some examples and try and present it to you guys to A, improve practical understanding of just the general key concepts behind compressive sensing, and B, encourage others to try to consider where in their applications, whether that be work or personal, whatever, compressive sensing could be of use to them. And so I'll say a quick disclaimer that most of the ideas in this thesis are not new. I didn't come up with any innovative developments or anything like that, but like I say, hopefully this will just be somewhat illustrative and informative in a general sense. So what is compressive sensing? Well, it's a new way of acquiring data which can be advantageous over traditional Nyquist constrained sampling. So there are three requisites that we need for sensing to work. Sparsity, whereby the majority of the signal's information is contained within a few significant coefficients. So basically, you can chuck away most of the information and still keep the core aspects. And we find that generally in our acquisition domain, we won't have a sparse signal, so we need to find some way to obtain that sparse signal. The second requisite is incoherence. So the sampling pattern in one domain doesn't necessarily correspond to that in another domain. So if we want to leverage transform domain sparsity, then we need to make sure that our sampling method is incoherent with our transform basis. Practically, this is done using sampling matrices which satisfy a property called the restricted isometry property. But practically, a very good way to do it is to use just a random sampling matrix. So that's pretty much what we did in this thesis, except I didn't use matrices, I just used array-based methods. And third is some form of optimization, which is just a way to try and improve the results somehow, which we'll discuss in due course. So when traditional Nyquist constraints aren't met, we get coherent aliasing. So this is just a tidy little example of that. We've got a 420 Hertz sinusoid sampled at 500 Hertz. And I assume most of us are familiar with Nyquist theory. So Nyquist theory would state that we have to sample at twice the maximum frequency in the signal. Here it is not. And so it appears spuriously in the red dotted line as an 80 Hertz signal. So if we have just an initial example of a double sinusoid, so a 4 Hertz and a 20 Hertz sinusoid superimposed, sampled at 100 Hertz with a Nyquist frequency of 50 Hertz. We Fourier transform and inverse Fourier transform to reconstruct the signal with and without thresholding. We get a pretty faithful reconstruction with some error introduced by the thresholding. So we can see in the middle panel there that there's only 2 peaks basically on either side of the Nyquist frequency. So it's pretty sparse in this domain, right? If we then decimate our signal, and I'll use decimate in a general sense. So if we decimate by a factor of 2, that's throwing away every second sample and so forth, to simulate a lower initial sampling rate. So again, we've got our 4 Hertz and 20 Hertz signals sampled at 50 Hertz with a corresponding Nyquist frequency of 25 Hertz. If we Fourier transform and then inverse Fourier transform, we get a pretty faithful reconstruction, but you'll notice that both at the top and the bottom, the signal looks a little bit different to the initial one, and that's because there's half as many samples. If we wanted to, we could do frequency domain interpolation by zero padding in the frequency domain and then inverse Fourier transform to get our original length signal back. And we did do that in the thesis, but I haven't shown it here. Now, if we then decimate further, so by a factor of 4, so that's throwing away 3 of every 4 samples in a sequential manner, we see that in the middle panel there, we do get coherent aliasing. So our 20 Hertz signal has been wrapped around the Nyquist frequency and appears spuriously now at 5 Hertz. So when we Fourier transform and inverse Fourier transform, with and without thresholding, the true nature of the signal isn't maintained. It's not there. So this just shows the original signal versus the reconstructions at 4 times decimation, regular decimation. Now, if we bring in the second requisite of compressive sensing, which is incoherence or randomness, at the top there, it's pretty unrecognizable. But in the Fourier domain, we do see the 4 Hertz and the 20 Hertz peak. But notice now that the coherent aliasing has been reduced to just random noise, which is spread across the entire frequency spectrum. So if we inverse Fourier transform with thresholding, we do get a somewhat faithful reconstruction of our initial 4 Hertz, 20 Hertz double sinusoid. So this sort of highlights the key that the thresholding is really a key step here. So if we want to be able to reconstruct from a lower sampling rate, we need to have our signal peaks well above the noise level so that we can threshold out the noise and just maintain what we want, just keep the peaks that we want. So we've seen that random decimation introduces random noise or spectral leakage as we call it. So we'd expect that if we decimate further and further, that we might get more noise, and that this example just shows that that is the case. So we've got up the top left 1.5 decimation, which corresponds to throwing out 1 in every 3 samples, 2 times, 4 times, and 8 times, and we see that the noise level gradually increases, and it seems to be a somewhat of an exponential type relationship. So sparsity also, if we decrease the sparsity of a signal by increasing the number of signal peaks that we want to reconstruct, then we also notice an increase in the noise level. And this appears to be a somewhat linear relationship. So this is a geophysics thesis. So let's apply it to a geophysical signal. We can see our example geophysical trace here and the corresponding magnitude spectrum. So notice we're now dealing with a transient signal, or it has short-lived features in it, which makes it a bit harder to reconstruct using Fourier. So if we randomly decimate it by a factor of 2, we can see the magnitude spectrum really suffers from that spectral leakage, and these high frequency air blast events here, they just get drowned out by the noise. So the reconstructions are pretty poor, as you can see from the bottom panel on the right there. What can we do about that? Well, we can try and lower the threshold so we can include more of the signal, but it's an apparent trade-off between lowering the threshold and including more of the spectral leakage noise that we want to avoid. So our hands are pretty much tied in that sense. We really just need to figure out a way to lower the noise so that we can see our signal peaks more clearly. So the next chapter of the thesis focused on some numerical considerations to try and reduce that noise. So one source of noise is quantization noise, which happens in the analog to digital conversion process, which is basically sampling digitally to come up with an approximation of what is actually an analog physical response. So this just shows the Fourier transform of, one way to reduce quantization noise is to just sample at a high rate. So this just shows the Fourier transform of a double sinusoid at various sampling rates. So as we increase our sampling rate, that noise floor decreases, and we can expect somewhere around a 3 decibel per octave noise reduction. So for every doubling of the sampling rate, drop the noise by 3 decibels. Quantization noise manifests at a pretty low level, so we shifted our focus to noise introduced in the integration of the e to the power negative I omega t function in the Fourier transform. So up to this point, our non-uniform Fourier transform has been a non-uniform discrete Fourier transform, which we just used a linear interpolation. So you can see the red points here represent randomly selected points that were kept. So where there are gaps between those red samples, we just hold the value until we reach the next sample. So because it's random, there's no guarantee how big those gaps are. And the longer the gaps are, the more noise is introduced in the integration of that function. So that's a zero order interpolation. This shows basically just an example of the FFT on the undecimated signal in the orange and the non-uniform discrete Fourier transform on a decimated signal. So that noise is due partly to the random decimation and partly to the integration error. How can we fix that? Well, we can try breaking up the random integration segments into a number of smaller subsegments. So that we see does reduce the noise, but it also reduces the signal peak. So we went down a bit of a rabbit hole looking at nonlinear thresholding to try and hug the shape of the noise to try and include the signals while chopping out the noise, but that didn't really lead anywhere. We could take it a step further. And if we, instead of just breaking up each randomly sized segment into a number of segments, we could break it up into equal sized segments, which would then allow use of the computationally advantageous fast Fourier transform. So that shows again, we do get a decrease in the noise, but also a decrease in the signal peaks there. We also took it one step further, and instead of doing a zero order interpolation, we did a linear interpolation, which again, we get the same effects, but I think the linear FFT does have a slightly reduced noise level compared to the peaks, so a slightly higher signal to noise ratio. And we refer to this method as the lin FFT method. So we've looked at the Fourier transform, but what about other transforms? Well, another transform that we might use is the wavelet transform. So the theoretical advantage of the wavelet transform over the Fourier transform is its property of time frequency localization. So whereas the Fourier transform is very good at telling you what frequencies are in a signal, the wavelet transform should be able to tell you what frequencies are in the signal and where throughout the signal's duration they occur. So it uses a wavelet analyzing kernel instead of an infinite sinusoid. So hopefully it'll give us a more sparse representation of our seismic data. So these are so-called wavelet scalograms of the same 4 Hertz, 20 Hertz double sinusoid signal. So there are a few things to notice. First, we notice that the 4 Hertz is to the right of the 20 Hertz component. And that's because the x-axis is a scale axis. So to characterize different frequencies, our wavelet analyzing kernel is dilated. And obviously you can imagine stretching out a wavelet, it corresponds to characterizing lower frequencies. So we could have flipped the scale and probably should have, but just didn't get around to it. You also notice that the 4 Hertz and the 20 Hertz, they're different magnitudes, even though the sinusoid was designed to have the same amplitudes for both. And that's because of wavelet bias, whereby at larger scales, the wavelet is more stretched out and has greater support in time, so it contributes more to the magnitude. So you see on the right there that we've accounted for the scale bias to try and even out those magnitudes. So this is the geophysical trace, the scalograms for the geophysical trace. And we can now see that we've got the main body of the signal, and also our air blast appears as a separate discrete event. So this just shows the undecimated and normalized, and the decimated signal randomly decimated by a factor of 2, and normalized wavelet scalograms. As with the Fourier transform, the wavelet transform is an invertible transform. So we can apply thresholding and then inverse transform to try and keep the signal components that we want. This is the result of that. So the 4 panels are using the thresholds shown in the previous slide. And I think some of them are pretty good, some of them not so good. And the plot on the right just shows zoomed in on the high frequency air blast event. So again, some of them are pretty good, some of them not so good. And this just shows that as we decimate further, the results do degrade somewhat. So I think we'd agree that those wavelet examples looked a bit better than the initial Fourier examples. And why is that? Well, we looked at comparing them. So we've got a signal with 4 frequencies, 10 Hertz, 40 Hertz, 120 Hertz, and 240 Hertz with amplitudes 1, 0.4, 0.2, 0.1, randomly decimated by a factor of 2. So our non-uniform discrete Fourier transform was able to get an FPP of the recovery, so comparing our recovered signal to the original signal of 0.9579, and the FPP is scaled from 0 to 1. The lin FFT method using Fourier got 0.9923, and using the wavelet transform, we got 0.979. So at the top there, I've just tried to show a few sectional views from the 2D wavelet scalogram to show the thresholding. So it looks like potentially there's something wrong in the way that we've implemented the wavelet transform, but we won't go into that too much. So comparing against for the geophysical trace, randomly decimated by a factor of 4, the wavelet is able to just outperform the Fourier lin-FFT method. So it's hard to say at this stage which method is the preferred one, and it's probably just coming down to something to do with the way we're thresholding. So to address the third requisite of compressive sensing, which was optimization, we looked at an algorithm called Projection Onto Convex Sets, or POCS. This was introduced as an iterative method for interpolating irregular seismic data using the Fourier transform, but it can be used with any invertible transform. And so the general procedure is we transform our irregularly spaced data to some transform domain, for example, using a non-uniform discrete Fourier transform. We threshold, as we've already seen, keeping only the largest coefficients. We inverse transform. So now at this stage, we'll have a regularly spaced signal, and we refer to this as our initial estimate. And then we leverage the data we've already acquired, and we reinsert the original random samples into our estimated signal, and then just repeat the process. So I'll show you this in action. Here's our 4-frequency sinusoid, and that bottom panel just shows the effect of the random decimation. You see quite a few gaps. Now this is our first iteration using the non-uniform discrete Fourier transform. We've got a fair bit of noise, and we can probably make out at the left here the first 2 peaks, but the 2 peaks that should be down here are just drowned out by the noise. So we've got our initial estimate in the orange there, and then initial estimate with the original samples, random samples reinserted there. Iteration 3. And we can see that the noise is pretty much just obliterated, and all 4 peaks sort of start to come through. So now that those 4 peaks are in the initial estimated signal, it sort of bolsters up subsequent iterations. So if I skip through again, you can see the peaks rise. So I'll go through that once more. There's the initial, focusing on the peaks at the top. And so this just tracks the RMS noise at each iteration, and we see that large drop in the RMS noise after the first iteration. And that's partly because we only have to use the non-uniform Fourier transform in the first iteration. Once we're back to a regularly sampled signal, we can just use a fast Fourier transform from then on, which we know has lower noise. And so I will mention also that we monitored FPPs. There are 3 FPPs there. If we consider our original signal as called 0, that's just the original signal. So FPP, and if we call signal 1 our initial estimate, and we call signal 2 our initial estimate, once the samples have been reinserted, then FPP01 is comparing the first 2, FPP02, which is the main one we're concerned with. It's comparing the original signal to the reconstruction with the samples reinserted. And we're not really too concerned with FPP12. It just monitors the difference between the estimate and the reinsert. So let's look at an example for a geophysical trace. So this uses lin-FFT and random decimation by a factor of 2. So here's our first iteration. It's already looking pretty good, to be honest. But we can see up here there's some blue poking through the orange, which we'd like them to overlap exactly. Skip to the next iteration. Next iteration successively gets just a little bit better each time. So I'll skip through those again. 1, 2, 4, 6. And so this just shows the reconstructions before reinsertion for a number of different decimation factors. And this shows the effect of reinserting into the estimate those original randomly spaced samples. This monitors the FPP values. And we'll notice an FPPD up here. We use this to denote basically just the FPP between the original signal and the linearly interpolated signal. So the random spaces have been linearly interpolated, which basically is saying this is what we get without using POCS. This is what we get using POCS. And so these are the improvements, and they're pretty insignificant, but at least they are improvements. So of course, POCS can be used with any invertible transform, so why not the wavelet transform? It's quite difficult to visualize the wavelet transform with all the thresholding. So I've just shown the FPP values here for the same signal. And once again, we do get slight improvements when we use the POCS algorithm over not using the POCS algorithm. So up to this point, we've considered subsampling in time, so throwing away random time samples, but what's probably more likely to be a benefit economically in geophysics is spatial subsampling. So we simulated random placement of geophones in the time-wavenumber domain. So basically, we just took a strip across a shot record, basically just treated it as a time series and Fourier transform it to get into the TK domain. So I've used a synthetic data example here. So if we look at this initial example, we took a strip at 0.175 seconds. We chose it because it's got significant seismic amplitudes. We've got a reflector there and some ground roll there. So decimation by 1.5 corresponds to throwing away basically every third trace randomly. So this is what our strip across the shot record looks like as just a time series basically. The bottom panel shows the random decimation. So I'll show first for NUDFT, and it took 11 iterations to meet our termination criterion. So there's the first iteration. So there's the top panel is in the TK domain. And then our initial reconstruction here is not looking too great. And then the reinsertion, arguably not looking too great either. There's the second iteration. We see the noise gets blasted away pretty well. And then skip to the 11th. So it's definitely an improvement. LinFFT for the same signal only took 2 iterations just because that's such low noise initially. So that's the second iteration. So we basically went on and just applied it strip by strip to a whole shot record. So we use the same synthetic model and look at decimation factor of, again, 1.5 to start with. So that's our shot record. That's what it looks like decimated by 1.5. I wasn't able to get rid of the traces in seismic units, so I've just zeroed them out. So hopefully you can see the effect there all right. This is our initial estimate. So after Fourier transformation and inverse Fourier transformation without the reinsertion. And that is post reinsertion. So I'll toggle between the original and the final result. Original, final result, original, final result. So I think that looks pretty good. Happy to be argued with. One way that we tried to monitor the performance of it was to, again, use the FPP, but we just monitored the final FPP. So however many iterations it took for the given strip, down the shot record, basically. So this is going down the shot record. So we see that towards the top of the shot record, I've actually omitted the first 40 because they were numerically intractable. But that as you go down the shot record, different strips will perform better or worse, depending on the frequency content that is in there. So let's look at decimation by a factor of 3 now. So this is our synthetic model again, decimated by 3. There's the initial estimate. There's the reconstruction with reinsertion. There's the original for reference. So you can see, looking at sort of a quarter of the way across from the left, there's that gap there that I think the algorithm gives it a red hot crack, but it really just can't get it. So now let's look at decimation by a factor of 5. So there are clearly some big gaps here. This is our initial estimate. This is our reinserted. That's the original for reference. Original, reinserted, original. So clearly there's some degraded results. Now what if we decimate regularly by 5? So that's what the shot record looks like. This is the estimate. And this is with reconstruction. Look at the original for reference, final result. it's a lot better. And it suggests that probably this model, even at 5 times decimation, is regular decimation, is not aliased. So probably not the best example, but yes. So recommendations, I think further testing on real data. Obviously, I sort of got to my breaking point towards the end of the thesis. I would like to get some more real data done, but didn't get around to it. Extension to 3D. All the literature is pretty much done in 3D scenarios. So I think there's probably something in that. I think it could be maybe work a bit better in 3D scenarios. Optimal random sampling. I just used a random number generator. So there was no constraint on maximum gap size or anything like that. And there's a bit of literature on this. So I think it's definitely worth looking into. Thresholding. We used hard thresholding, but there are other methods of thresholding that can potentially yield improved results. And like I mentioned, I think we didn't quite hit the nail on the head, or I didn't quite hit the nail on the head with the implementation of the wavelet transform. So could be room for improvement there. And also other transforms. So there are a whole range of other transforms that are actually designed for gaining a sparse representation of seismic data. So that would probably be something worthwhile looking at as well. Thanks very much. Any questions?
Got about 2 minutes for questions before we swap over. So you can ask questions now. Anybody?
It's all good. We don't.
So,
Go on.
what do you see? I mean, this looks like wonderful money for old rope. What are the main risks?
Risks, I'd say practically it's all very new at the moment, so there's still a bit of uncertainty. But I think, yeah, sort of just designing it, figuring out what sort of thresholding would be needed. Obviously, these are very simple examples, and it's been done in practice quite successfully, but with much more complicated mathematics and stuff than what I've done here. I think probably at this stage it's still a bit experimental at this stage. The maths is there. I just couldn't understand it.
Anybody else? Okay, thank you. And I'll now hand over to Dale.
Thank you.
Hey everyone, let's do this. So I've been working at Belsos since late 2019, doing research and development as a field geophysicist, and I've had some extra time to work on this project post thesis, so there's a little extra stuff in here as well. At the beginning of honours, Steve proposed this project to me, given my obsession with Antarctica and his interest in earthquake seismology, so it was a fitting topic. So firstly, I'll be introducing the concept behind P-wave receiver functions, their character, how they are affected by the presence of an ice sheet. The ice sheet modeling process includes different concepts which have helped us to construct homogeneous ice layer models. The concepts include estimating the velocity ratio and a generalized linear inversion. Derived ice parameters are thickness and body wave velocities. Using the derived ice models, we have trialed 2 deconvolution methods, Wiener and predictive, and tested these with synthetic earth models. Using the derived ice models, the results of the synthetic trials justified the methods to be trialed on real data. The original thesis data were only collected at a single station in East Antarctica. With continued work, we've been able to perform the same processing on 2 more stations, one in West Antarctica and another in Greenland. P-wave data is the most desirable signal to process in earthquake seismology. This is primarily due to the fact that P-waves always are the first phase to arrive at a given receiver station. This means good signal to noise. Depending on the epicentral distance between the source and receiver, other phases will arrive later and interfere with the P-wave coda. The earthquakes I have processed were often 20 seconds to 1 minute of uninterrupted P-wave signal, followed by the outer core reflection, PCP, and the source side reverberation, little pp. As the wave approaches the receiver, we assume the wavefront has approached as a plane wave and the wavefront travels through the lithosphere. Waves are converted and internal reverberations occur at layer boundaries. One of the most common waves to study in the Moho is the P to S conversion at the base of the crust. The converted wave will arrive after the initial P wave. These phase arrivals are shown as peaks in the receiver function. The receiver function is a form of deconvolution by spectral division. However, the final product being analyzed in the time domain. For an incident teleseismic P wave, we deconvolve the vertical component from the radial. This theoretically removes any source-related signatures which are present in both components, leaving behind the phase conversions and reverberations within the crust below the receiver. Note that the P-wave receiver function will only show shear wave-related events, with the exception of the first peak, which is the P arrival itself. To show the character of the receiver function, we'll have a look at the output of a single layered crust above a mantle half space. Here I've just used an average body wave velocities and densities for a 40-kilometer thick crust. The first peak to arrive at 0 time here is the direct P wave arrival. The following peaks in the function are the phase conversions and reverberation lag times due to the direct P wave arrival, with respect to the direct P wave arrival. The second peak is the converted S wave from the base of the crust. In fact, the P to S conversion from any superficial layer in any environment will always be the first arrival. Note that the Moho Ps always has positive polarity. The third main peak is a reverberation. 2 passes as a P and 1 as an S, and so on. The only direct converted or transmitted phase is the P to S. All the rest of the events are multiples and converted phases at reflection boundaries or harmonics of other events. The amplitude and polarity of the peaks are dependent on the layer densities and body wave velocities, more appropriately, the acoustic impedance contrast at the layer boundaries. With the addition of an ice sheet, the receiver function immediately becomes much more complex. Here, the PS phase from the ice, again, is the first event to arrive after the initial P wave. What is problematic here is the amplitude of the events due to the ice. Recall that this is controlled by the acoustic impedance contrast. In general, ice has a density just over 900 kilograms per cubic meter, which is significantly less than any bedrock basement density. This large contrast boosts all amplitudes and transmissions and reverberations at the base of the ice. For this model, there is an ice phase destructively inferring with the Moho PS phase. This phase, which has traveled through the ice 5 times, is stronger in amplitude than the converted S phase from the base of the crust. As you can see, when I remove the ice, the Moho amplitude is much weaker. Just note that the time shift present here, that there is a time shift here, and that's because we are adding ice and that extra time traveling through is accounted for in the receiver function. Even though we've seen how complicated the receiver function becomes on an ice sheet, the repeatability of the ice phases in real data is quite pronounced. Here are P-wave receiver functions of 14 different earthquakes recorded at Concordia in East Antarctica. While noise in the receiver function obviously differs, the strongest peaks match well, even up to 7 seconds. After seeing these results, we began to plan if we could model the ice based on the lag times of the ice phases, as the lag times were so consistent. Stacking of the receiver function also boosted these events. To begin ice modeling, a useful physical parameter to estimate would be the velocity ratio in the ice sheet at a given station. We thought to use the gamma equation since we were able to estimate 3 out of the 4 unknowns. The unknowns being TP and TS, the layer travel times for the P and S waves and their respective angle of incidence, IP and IS. The first step is to solve the layer travel times for the P and S waves. These are computed from the peak ice phase lag times in the real data receiver functions. For example, the PS phase lag time, tau PS, is the P travel time minus the S travel time. We only need to find 2 lag times in the real data to solve for TP and TS. We also need to know the incident angle of the incoming P wave, which is estimated using hodogram analysis. This is done by analyzing the first quarter cycle of an incoming teleseismic P wave. The vertical and radial components are plotted against each other to measure the incident angle, and just measured directly. The final unknown is the S incident angle. Since IP and IS are directly related by Snell's law, and here the cosine quotient in gamma does not change drastically for small angles, we simply just guess the quotient and iterate over new calculations until the quotient converges. Once the quotient is computed, we now have gamma. However, we still don't know the ice velocities themselves and the thickness of the ice sheet. To find these desired parameters, we have implemented a generalized linear inversion process. The known parameters are the receiver function lag times, which relate to the ice sheet, and the ice thickness VP, VP and VS are the unknowns. Lag times in the receiver function are all functions of the layer travel times. Again, the same example here of the P to S phase is the travel time of P minus the travel time of S, as described earlier. Using several picked lag times from the real data and a starting model PRF, we set up an overdetermined system of equations. The known Y vector contains the differences between the starting model lag times versus the true lag times. The starting model is perturbed for each unknown to build the Jacobian with central finite differences, and the unknown vector X contains how much the parameters were perturbed. We solve for X with singular value decomposition and update the model, and we iterate until the problem converges. We are still exploring methods to constrain the inversion since non-uniqueness is an obvious problem. So far, using the estimate of the velocity ratio, we have been able to constrain VS. So now the problem is only dependent on thickness and VP. Overall, the constraint inversion process results in, they have appeared to produce realistic ice wave speed velocities, so it's plus. Furthermore, we've been able to compare thickness estimates with known drill core measurements in all the ice sheet stations with minimal error. These results are the average of the inversion output at all receiver functions at a given station, i.e. we computed the inversion step for each individual receiver function prior to stacking. The final velocity estimates vary between stations, but we're not out of range of known ice body wave velocities, that being between 3.8 kilometers per second to 4,000 kilometers, 4 kilometers per second for P waves and 1.8 kilometers per second to 2 for S waves. Even though the results from the inversion process are non-unique, the final ice sheet model receiver functions were close matches to the real data. Now we trial filtering to remove the ice sheet responses from synthetic model data. Wiener deconvolution, aka signature decon, can be used to compress a known signal to a spike at time 0. Here we have used the ice model receiver function and filtered the PRF to only be the 0 time peak. This is shown in figure A, with the original receiver function in blue and the desired output in black. The filter designed in this process was used in the following stages. Figure B, we have applied the filter to the receiver function with an ice sitting on an average crust model, so just 2 layers. From the original function in blue to the filtered version in black, we can see a major reduction in ice sheet reverberations. In figure C, we changed our crust to be a much more complicated realistic model, and we see a similar result. The filtered functions of the crustal phase is very low in amplitude, so I'm just zooming in to show you a little more detail. The gray dashed lines in figure B and C denote the three first Moho phases. An interesting advantage of this filtering is that the Moho phases have been shifted into their true lag time positions as though there was no ice sheet. This is an intrinsic property of the Wiener filtering method, compressing all ice sheet information to the zero time peak. Unfortunately, some artifacts remain after filtering, and several are of notable amplitude, which could be confused with true crustal phases, just like these two next to the Moho Ps here. We are still exploring how these artifacts came about, but one key assumption should be considered in this problem, the convolutional model. We know that a multi-layered receiver function doesn't satisfy this model. The synthetic ice crust PRF in blue with the convolution of the separate receiver functions shown in black. As you can see, they're not equal. However, there is consistency within the results, and this is especially with the main peaks. And this is why we are seeing some successful attenuation of the ice sheet in the modeling. Since some artifacts remained after signature decon, we wanted to test another method. Predictive deconvolution is commonly used in the industry, even in situations where the method's assumptions are not strictly satisfied. This is also the case for this problem. In the context of reflection seismology, the basic assumptions of predictive deconvolution are random reflectivity, a minimum phase wavelet, and no noise. Unfortunately, none are satisfied here. In figure A, we have the ice-only model, PRF, with predictive deconvolution applied. The prediction gap is the second zero crossing of the autocorrelation with a filter length of 40 seconds. Immediately, we can see that this hasn't been 100% successful like the Wiener filter. However, when applied to the ice crust PRFs, we see some interesting results. Here, there is no time shift like the Wiener filter, but the crustal peaks are of greater amplitude, again denoted by the gray dashed lines for figures B and C. The predictive decon appears to struggle suppressing the initial ice crust, the ice phases early on before the Moho Ps. This makes, and it doesn't even affect the PS phase at all. And this makes sense because the ice PS isn't actually a reverberation. It's not a repeat. It's its own transmission. So the predicted decon is actually seeing that as its own event. So it doesn't remove it. Also note that there are some spurious effects here too, like this negative peak at about 2 seconds. And that could be damaging to true crustal phases as well. We were satisfied with the preliminary synthetic trials and tested both decon methods on real data. Here are the Wiener results for the 3 stations of trials so far. Again, the original PRF stack is in blue and the filtered results are in black. Obviously, with real data, we have significantly more noise present within the receiver functions. However, after filtering, the known ice phases have been drastically reduced. So much lower in amplitude in general for the first 10 seconds or so, where the ice phases are dominant. Here, the gray dashed lines are just an indicative range of crustal thicknesses I was looking for. So the first dashed line is approximately 18 kilometers, like the Moho depth, and the second line is 55 kilometers. So I'm trying to pick a positive peak within this range. And as you can see, well, those peaks aren't much greater than the surrounding noise. So it's very difficult. But let's just go to the next slide and have a look at the predictive decon. As expected, the early ice phases were not reduced as well as the Wiener process. However, within the expected Moho Ps range, there are standout events for Marybirdland and Eamon in Greenland. Unfortunately, Concordia can't really be interpreted. This could be due to the ice sheet being much more thicker there, and that meant that there's longer ice lag phase times. So the crustal Moho phase is within a range where the predictive decon is more destructive than it should be. But that's just one idea. We haven't been able to show that directly yet. These are the two peaks that we're picking as potential Moho peaks for the predictive decon. So if you recall, the time shift for the Wiener filter was shifted back by the ice PS phase, and not in this case, right? So if we actually look back to the Wiener filter process, if these peaks are true, then we should expect that the Wiener filter might have peaks in the time lag negative of the ice PS phase in the Wiener deconvolution. And to our surprise and sadness, we got both results. So Greenland here was actually in exact agreement. So that peak here, which actually is the strongest positive peak within the range, is in fact the exact the exact time shift away from the predictive decon result. But for Marybirdland, with this large peak here, a significantly large peak too. So we were hoping that that would be the case here, but it's actually the largest peak in the Wiener result is 2 seconds behind, which is almost 2 times over the time expected. So a few inconsistencies in the results here, unfortunately. This table shows picks from the previous, shows what we picked from the previous 2 slides, just summarized. For each of the methods, we can derive the approximate depth range, an approximate depth range dependent on the incident angle. The Concordia results are based off just the Wiener pick, but show a depth range that was within ballpark figures of other studies. Marybirdland has a larger range because, well, the method produced different results, so I had to account for that. However, other studies are still in disagreement about the crustal thickness there, and this range actually encompassed all of those. So that was interesting. And the Eamon results in Greenland, they just agreed perfectly, and so I've just given a rough estimate there. I didn't exactly find some stations that had an exact, well, not exact, that their interpretation for the crustal depthness there, I based it off an interpolation, but that was within a interpolation map, but that was within this 40 kilometer to 43 kilometer depth range, which was kind of exciting. In conclusion, we still consider the methods to be successful at attenuating the ice sheet reverberations, more significantly with the Wiener deconvolution. Predictive decon may be used to assist with picking the Moho phases, but it isn't as robust. Note, however, this is not conclusive, but it is just interesting that these numerical methods are producing ballpark results compared to other more complicated methods. Cheers.
Any questions?
Nick?
Now, you're saying that there's more complicated methods out there. This seems fairly, I don't know how long it to get this out, but there's complicated methods that take a long.
Well, I was never able to test them because they were so complicated. I didn't have access to those algorithms, but the Wiener deconvolution and signature decon, we've all programmed by hand in class. So they're very simple. Obviously the data collection was the most complicated thing in this whole thing, and the receiver function processing in itself, but just too many boring, gory details to list here. But all of the receiver function processing aside, the more complicated methods, they wavefield decomposition, and there was, and then just completely alternative methods as well. Like you can look at an S-wave receiver function, which is looking at the S to P conversion at the base of the crust instead. So, but that's a different process altogether. But I did have that in the thesis too. But since we've moved on with the simple deconvolution methods, the primary focus has been on that for the time being. Yes. I wish.
Keep trying.
Just having Antarctica in the title of the thesis is a step. That was my idea anyway. Yeah.
Okay, let me swap places with
Yeah.
you.
Makes sense.
I'll finish the webinar by saying thank you to those that joined. Let me try and find that. There we go. So yeah, thank you for those that joined on the webinar. Hopefully we'll be doing more ASEG Queensland live streams of our talks and be recording them. Thank you for joining this time. We'll see you next time.